All right. Thanks, everyone. I really appreciate the opportunity to speak here. My name is Brian Sturtevant, landscape ecologist out of the Northern Research Station out of Rhinelander, Wisconsin, also on the Lake States Fire Science Consortium board. So one of the things I really appreciate about this meeting is I get to meet all of you. And so I really appreciate the opportunity to speak here. We're going to go in a little bit more deep dive into a specific study. This takes place up in the Moquah Barrens. I wanted to acknowledge this is a large team effort, so this is certainly not myself alone. Crystal Kern, Randy Kolka, Matt Dickinson, Dion Donner, all from the Northern Research Station, as well as Jessica Meisel and Kathleen Quigley out of Michigan State University. And we've got colleagues of the Chequamegon-Nicolet National Forest, Brian Haringa and Matt Bushman, who's now back at the Chequamegon-Nicolet. This is research that's funded through the Joint Fire Science Program. And so this is the Moquah Barrens restoration area. It's a very exciting place where we've got, there's been restoration that's been occurring here over the last 60 years. And it originally took place in much smaller burn blocks, but they've since aggregated those burn blocks over time to be what you're looking at right here. This, you see this RNA, this research natural area is a square mile in size to give you a sense of scale. And so these burn blocks are on the order of anywhere between 800 to 1,500 acres in size. These labeled burn blocks are the ones that are part of this study. And in part, the restoration really initiated for the restoration of this sharp-tailed grouse habitat, but it's since expanded into the realm of ecosystem management. And so the goals here are to restore this mosaic of pine, savanna, woodlands, and barrens to give you a sense of what the barrens are like. They're kind of this ericaceous mixture of grasses and herbs and these low shrubs such as sweet fern and blueberries. It would be in kind of the classic stage there. Then you've got that mixture with a deciduous forest, these heavily thin conifer woodlands that have been thinned to be to create much more openings for the Eli, if I could, is there a way to change the because right now I'm just looking at the slide as opposed to the other method.
Actually, no, because
no
this is the, we could, but then they'd see your presenter view
Oh,
over there.
All right, well, never
Sorry,
mind.
Brian.
I'm going to wing it.
Yeah, without your notes.
That's right. We're all in an adventure today. So, some of the processes that are influencing this, of course, is Greg Nowacki's work looking at mesification. It's an important process that's affecting this landscape. And so when we talk about where the Moquah Barrens is, it's really in this woody densification stage where you have increasing woody encroachment. And some of the issues associated with that, of course, include the buildup of the forest floor, as well as the encroachment of hardwood stems. And so woody encroachment management is part of the real challenge. Any of the species that are out there have the ability to sprout vegetatively. And so there's two real main management prescriptions they use to battle that. One of those is prescribed fire. The other is this brush cutting practice where they brush cut it the season before, allow that to cure. It's kind of a 1-2 punch method of trying to impact that more severely. And so by allowing that to cure over a season, that should allow that to burn a lot under much hotter conditions. And this is something that we could then manipulate as part of our study. And so really what we're looking at in terms of this study is that either prescribed fire alone or the combination of brush cutting and prescribed fire. And so this is kind of a schematic of the successional processes that are affecting this landscape. And so this kind of open canopy woodland barren severe that was there historically, maintained through surface burn regime. And back in the 30s, when this area was begun to be incorporated into the national forest, there was a lot of actual direct planting of those open conditions because they were the easiest to plant. And so some of that conversion to this pine forest was very intentional. Some of the unintentional successional stages, there's some of that conversion to pine forest, but a lot of it is moving towards this hardwood forest. So the question is, in their burn treatments, when you add that enhanced fuel, is there the potential to push it stronger in that direction through soil heating? And in theory, that's true. There's a few things that more intense soil heating could accomplish. It could be that you decrease the duff thickness through consumption. It could be that you're decreasing both soil moisture and nutrients as a consequence of that. Damaging below ground woody tissues is a possibility, and potentially also favoring fire adapted species in the seed bank. So all those are part of this particular study. And so in terms of the cover types that we included in the study, deciduous forest, of course, a deciduous forest history, at least pole-sized tree in a canopy closure situation. Then this pine woodland treatment. This is a common treatment that they have out there. Pine plantation history, where they've opened it up, the target basal area on the order of 30 to 60 feet per acre. This is all done fairly recently, on the order of between 2010 and 2015, and intentionally removing the biomass from that so they didn't leave behind a lot of the wood, so they wouldn't damage those standing trees. This is that transitional stage, that brush stage, and what we use as our criteria was their own trigger points that they use for management. So 70% cover and brush, they'll use as their trigger point for brush cutting. So that was the typical target. We did go down to on the order of, say, 50%. And these all include the tall shrubs, hazel, it can be birch, red maple, a lot of aspen and oak. But it excludes the short species, so the more barrens adapted species, sweet fern and blueberry. Barrens, the official we use as our definition is less than 50 trees per acre, or a basal area less than a woodland. So it's really either a savanna condition or an actual open barrens condition. And again, excluding those short shrubs. Here are the fuel treatments that we applied. So that we had brush cut and leave, they were leaving on the order of about 10 tons per acre. And so you have a sense of what that fuel load looks like there. And then in some of those sites, we went in and we removed the brush. We also had a standing brush kind of control to those. And then within the pine woodlands, we had the existing low fuel condition, and then we added fuels to be about the same level of brush that you see here. And then a Barrens, here's an example of a Barrens fuel addition plot that you see here. We had either contrast between no fuels and added fuels. The scale of these, the plots are about a 20-meter radius or one chain, so about a third of an acre. So any of you doing the math out there, 10 tons per acre, that's about 3 tons of brush, and about 20 treatments times 2 burn years. You do the math as to how much brush we actually moved. And so this would be our overall study design that we applied. And so we're looking at the cross between what the historic state was, and our definition of that, what was mapped in 1951. So either pine, primarily pine plantation, or deciduous or barrens. And then the current state, is it in that woodland state, brush transitional state, or is it in a barren state as well? And then within that are fuel treatments. And of course, we didn't have fuel treatments across the whole spectrum, but you see most of that spectrum is covered. And that was applied over 2 different years, 4 different burn units, about 4,000 acres down. We also included reference plots. So these were intended to capture the bounds of Moquah conditions and serve as non-burn controls for those restoration stages. And we included in that 6 different vegetation types. So closed canopy hardwood forest, closed canopy natural pine, pine plantations, recently thin plantations, those brush transitional stages, as well as open barrens. And just for reference, looking at the duff thickness, you can see that barrens conditions have traditionally less duff, but we're not really talking about very deep duffs, on the order of about 1 inch on average, and there's a lot of variability there as well. So this is kind of an overview of what that looks like in terms of our distribution of plots over 2 years. And this would have burned in 2016, plots burned in 2018, and then our reference plots around the perimeter. You can see what that looks like on the ground the day after the burn there. So this would be block D that was burned. You can see here are the footprints of our brush addition plots. So that you can see the ash, what we call our ash crop circles that were left behind after the burn. And this is our plot layout for that. And so we had, we were measuring standing trees. We had our fuel transects. We're measuring shrub and saplings along these transects as well. And then we had these quadrats, either for our soil sampling or our seed bank sampling, and along those transects. And that's also where we quantified fire severity on those quadrats. And so that would have been measured using duff consumption pins to get it either duff and litter consumption. We had co-located paint tags to get it maximum heat. And we, on a subset of those, sampled ash as well. And then we did our application of our severity. You can see the paint tags that were located here. So they work in terms of, we certainly got good fuel consumption. So you can see here the effects of or the amount of fuel consumption in terms of light fuels consumed. So here are brush additions on the order of between, say, 5 to 12 tons per acre of fuel consumed. And our removals did a pretty good job of getting it down to those ambient fuel levels. In terms of our maximum temperatures, and we had pretty good contrast in heat. And so some of our paint tags, the aluminum that held the paint tags, has a melting point of about 661 degrees C, and that's a melted paint tag there. So we certainly had some of those observations. And some of the consequences of those enhanced fuel, it tracks pretty well with our fire severity classification. So this National Park Service severity classification, no burn on the left there, increasing severity as you go to the right. You can see how that tracks pretty well with the amount of light fuels consumed. If you look at the calibrated consumption, and I'll talk a little bit about that later, but the how that tracks with the surface paint tag temperature. So we're certainly increasing our temperatures, again, up and above that 600 degrees Celsius mark. And then another consequence of this, of course, is you're getting increased ash loads in those locations as well. And so that tracks pretty well with our paint tag and data, as well as our consumption data. There's some consequences of those enhanced fuels as well above ground. And so this would just be an example of a plot that was actually burned in 2016. And then I took this photo after a second burn in 2019. You can see all the jack pine is dead. Jack pine wasn't all that hard to kill. There was actually a lot of mortality, whether you added fuels or not, in the jack pine. But red pine, there was some pretty significant mortality in these fuel addition plots versus a regular, more benign surface fire under red pine. You can also see the abundant, this is now recently top killed red maple coming up in the understory. So even though there was a brush addition to that, there's still pretty significant brush in the understory. And so what does this mean for soil heating? We got our heating contrasts. And so there's some pretty good study about this kind of work. There's a nice contrast by Hartford and Franson looking at the contrast between our situation of slash over moist duff, which if you think about spring burns, which is what we're doing here, is typically a more moist duff situation. And that contrasted with litter over dry duff. And what you see is that you can certainly produce large flames, you get a lot of heat from those, but you get very minimal duff consumption under those conditions because of the duff is acting as an insulator. But if the duff is dry, it can actually burn independently. And if it does, that actually drives heat down very well. And so under that situation, you get a lot of soil heating. So the question is, where in our situation we fall with these spring burns in Moquah? So the data sources for this talk, we're looking at two different kinds of soil thermocouples. We have the thick thermocouple that's in the flame, that's calibrated for these different kinds of kind of fire behavior, so fuel consumption, fire line intensity, flame residence time. And then we have the thin thermocouple that's buried in, so it's at the interface between the duff and the mineral soil, and that's measuring your soil heating. And those were co-located on these quadrats. And so what we're actually looking at is not the average plot level data, but we're actually looking at the point level data that I'm going to show you here. And so this is summarized across both burn years. And what we're seeing is that we get some pretty good range. So the fuel additions did what we wanted it to do. You can see the difference in fire behavior between kind of a maintenance burn over the barrens versus that really intense burning that you see in a brush addition plot there. And you see consequent differences here in the amount of consumption as well as the amount of intensity that you see. There's quite a range there. So we got the contrast that we wanted, which was what was important. In terms of our actual temperature rise, which is the variable that we're interested in, on average, about 93 degrees C. So this is important. To get to significant damage below ground, you need to breach at least 60 degrees C. So that's the threshold for any biological damage. So we did exceed that, but a lot of that is towards the tail end. So a lot of the temperatures that we measured, really there's a lot of low burn and then a few on the high end. The average of that comes up to just above 60. So we are seeing some damage below ground, but it's spotty in terms of where you see it. In terms of your duff moisture, we're looking at about 50%, but of course there's a lot of variability to that as well. In terms of duff consumption, one of the variables that we're really interested in, not very much, about 1/4 of an inch on average. So we're not really seeing a lot of duff consumption. So if you look at what are the controls on soil heating, we did not find any evidence for independent burning of the duff. So that's not really contributing as a factor. So the two factors that really are controlling whether or not heat penetrates below ground is the amount of fuels that you have above ground, and then the depth of the duff acting as that insulation. So this is precisely where we are. And so we find that duff certainly is a great insulator, but only if it's thick enough. So if you have that condition where you have thin duff and you have high woody fuel loads, you certainly can get at that condition of high soil heating, but in that dormant season condition, it acts as a very good insulator. So the next question is, how effective are those spring burns for decreasing shrub densities? And we find in terms of top kill, very effective. It caused near elimination of all the hardwood stems across the board. In terms of below ground, not really effective. And so if you look at this initial density of sprouting, we get almost 100% top kill, but by post year, 1 year later, you're right back to the same densities that you were. And this didn't vary depending on the fuel treatments or anything else. It was very, very consistent. And this perhaps should be expected. So these are actually, I believe, photos from the same experiment that Brian mentioned in his presentation, showing the difference in terms of hazel densities from that study due to a dormant season burn. And so it's, in a way, it's something that we know, but important to see whether or not there's any influence of these wood subsidies. In terms of whether or not there's any effects on seed bank density, really minimal differences. And so we're looking here at the number of germinants that we saw after growing the seeds out in the greenhouse, and essentially no effect before versus after in terms of the effect on the number of germinants. So we're not seeing that. We do see that there's more seeds in the duff layer versus the mineral soils, really insensitive to the treatments. The most diversity or differences in composition and numbers of germinants really had to do with what the vegetation type was rather than the treatment itself. So why do we not see a stronger below ground response? Well, first of all, heat rises. It's hard to get heat to penetrate down. And so anyone who studies below ground effects knows that it really doesn't, most of the effects is going to be right at that surface layer. And we see during these spring burns that the duff is cool and it's wet and it really acts as a very good insulator. And so that protects both the rootstock as well as these buried seeds near the surface layers as well. So just a little bit of food for thought. This would be a comparison. You're just looking at what it typically looks like. So it's very easy in the dormant season to get black. There's no doubt about that. This would be by comparison, kind of the more typical spotty, inconsistent burning that you see during the dormant season. But this is the seasonal long temperature that you see, of course, the range of the season. And so the difference, the ability to get to that 60-degree mark in terms of damage below ground could be easier in the summer. So just, again, food for thought. So next question is whether or not it improves soil conditions for native barrens plant communities. And so the data that comes for that is these nutrient exchange rates across all of those different nutrients that we're looking at, nitrogen mineralization rates using these those incubators here, the forest floor and mineral soil chemical properties. These are the variables that we're looking at. And then soil hydraulic conductivity, which gets at the kind of the residence time or the ability of those soils to retain moisture. And so based on our existing understanding of the system, it's kind of a cartoon of what we might expect. And so you think about if you continue to apply fire to these semi-open systems, you would expect to have low soil fertility in these very sandy soils, which would retain those open systems, and you'd have low duff, which means low water retention as well. If you exclude fire, you'd expect eventually a buildup in those soil nutrients over time. You have that brush encroachment, canopy closure, and you'd expect to have higher water retention under that as well. And so the hope is that by repeated burns, we would get back to this open canopy system and reduce those nutrients as well as that moisture retention, and that should be an easier thing to retain over time. So an important thing to think about in terms of nutrient dynamics below ground is that those chemical transformations are temperature dependent. And so what that means is that charcoal and ash, that all forms at these lower temperatures that you see here along this gradient here. So this is your kind of black ash to white ash. And the reason why it's white is because ash is generally enriched in cations. So things like calcium would be deposited because it takes much more higher temperatures in order to volatilize that. Whereas things like nitrogen have lower temperatures. So we're in the range here that we might see some nitrogen volatilization depending. So what do we see? Now again, the general expectation here is that you'd expect to see a post-fire pulse due to the ash deposition, followed by a decline in nutrients because of these processes. Within the sandy soils, you'd expect a lot of that to leach out over time. So we know that ash is an important post-fire soil nutrient source. And there are important differences in the composition depending on what kind of fuels you're burning. But certainly you see a lot of calcium in the soil, in the ash, as well as nitrogen deposited as well. So in terms of loads, these are some things that we've quantified. You can get on the order of about a ton per acre, or excuse me, a ton per hectare, all enriched in those nitrogen and cations. And so if you just look across the board, we see that pulse where you get that increase in nitrogen that just immediately post-burn, and then you begin to see a decline as soon as a year post-burn. That just indicates there's either rapid uptake by the plants or leaching through the sandy soils. Burn severity does appear to have an influence on that. So the higher your severity index, the lower the amount of nitrogen that's left over. So that does indicate that you might have some volatilization under those higher temperature conditions. If you were to compare burn units versus unburned controls, we do see that you tend to have higher nutrient stocks in the unburned reference plots than you do in the burned regions of the study area. In terms of some of your important cations like calcium and magnesium, in this case for calcium, we actually see an increase in calcium that tends to build over time. So that's an interesting result, and I'll get back to that. Whereas magnesium actually tends to deplete over time. And so these are both important for plant growth. There's also the potential for legacy effects. These are below ground. And so one of the things that we're interested in was whether or not vegetation history had any influence on some of those processes, or whether the heterogeneity in burn history had any influence. So if you recall, those smaller burn blocks were then aggregated to these larger burn blocks within our study. And so we could use that heterogeneity in burn frequency to see whether or not it had any influence on some of our response variables. Well, that's interesting. I've never seen that. All right. So we have horizontal transfer of water, apparently, in our hydraulic conductivity. And essentially what that is measuring the rate at which water seeps into the soil layer. And so it gets at this question of how much that water can enter the soil, how rapidly and how rapidly it drains. And so if you have, if it holds on to it, if you have low conductivity, that means it can hold on to that moisture longer, right? So what we see is that time since burn has an important influence on the rate at which the soil is able to drain, or that water is able to drain out. So that means that your unburned reference plots have greater moisture retention than your burn plots. We also see that it has a positive relationship with burn frequency. This is dependent on the amount of soil moisture. So if you have very dry soils, those are actually resistant to absorbing water at all anyway. And so we do see a difference in very dry soils versus soils that have, some moisture as well. Okay, but within wetted soils, you see that unburned sites tend to retain, these unburned sites tend to retain water longer. And so you see that burn frequency and time since burn have an important influence on the ability of these systems to retain water. A few other things that make you go, okay, so these are just things that some of these other responses made good logical sense to us. Some of these others, we said, those are interesting. We'd like to investigate those a little bit more. And I just want to bring some of those to your attention. So one of those is that pine history seems to enhance the development of the forest floor more rapidly than some of the other cover types. And that tends to persist in restored barrens that were restored from sites that had plantation history. So that might have some influence on some of the choices that you make down the line. There's some indication of elevated nitrogen within barrens that might be related to nitrogen-fixing plants. So sweet fern's a very common plant species out there, and it is a nitrogen fixer. So that may increase nitrogen in some of those barrens communities. Cation stocks were generally elevated within brush sites, and so that transitional stage may have that kind of a positive feedback loop that may be a little bit of a challenge below ground as well as above ground to battle. And then soil cations affecting fertility seem to be enhanced within locations affected by frequent burns. So what this suggests is that over time you might be building up additional fertility through repeated burns. Few basic take-home messages, my 30 seconds left. We have brush cutting practices, increased fire intensity, above ground severity, and ash deposition. We found that duff consumption and soil heating were minimal. Sprouting trees and shrubs were very resilient to top kill only disturbances. That late dormant season burn really had minimal effects on woody stem composition and density. In terms of the seed bank, the duff and upper mineral soils are certainly seed sources for common plants. We didn't see really any effects of the burning on the below ground seed bank. And then in terms of the rare plants, we really did not see many of the rare species in that seed bank. And so that has some suggestions for seeding as well. In terms of soils, soil nutrients respond to fire, but the effects of a single burn are minimal and ephemeral. The legacies of past vegetation management does appear to persist below ground, and the repeated burns may be necessary to condition the soils towards that more archetypical barren state in terms of lower nutrient stocks, thinner organic horizon, and higher hydraulic conductivity or lower water retention. And with that, I just want to acknowledge the Shawang and Nicolet National Forest and all the partners that we had for the study, and the funding sources and the other people that were involved. With that, I will end.
All right, next up is Patrick Johnson.